so we can do that. All right, so what we're going to be doing with our text preparation, right? We're not working with like strings containing numbers, or we're not cleaning up the data, but we have raw text. So let's jump right in, and we're going to talk about what do we do once we have our fully acquired raw text. There's a lot of different tools that we could use to handle the text. One of our tools that we're going to use is a library from Python called, or a library for Python called NLTK. That's short for Natural Language Toolkit. And this Natural Language Toolkit, this has a whole bunch of functionality. We're just going to borrow a little bit from it for this lesson. And I want to preface what we're doing. We basically have a workflow for parsing our text data, and it's going to take about these 6 steps, much like how the data science pipeline is a general overall idea of how to approach things, but it doesn't mean that it's very super duper rigid, right? Same deal with text parsing and text normalization. So let's talk about what some of these main big steps are and why this matters. So first thing that we're going to do when preparing our text is lowercase everything for normalization. Now, there's a couple of ways of thinking about this. Most of the time, almost all the time, a capitalized version of a word is not different than a lowercase version of the word. So the key idea behind normalization is we're reducing variability in the body of text, so that with the understanding, or with the assumption that by reducing the variability, like uppercase versus lowercase, that we can have our text kind of converge. So the word, let's just say carrot, and the word starting with an uppercase C for carrot, those are talking about the same thing. So lowercasing everything makes sense. There's of course an exception to every rule. The exceptions to when you might want to keep your text uppercased is if you are specifically using an NLP tool that is specifically looking for uppercase words, like if somebody's using all caps, for an example. But usually we want to normalize our text to reduce the variability. Okay, so we'll lowercase all the things. And another space where we're reducing the variability so that we can cook our text down a little bit further is a process of removing any accented characters or any non-ASCII characters. And again, this isn't like these rules aren't coming down from the mountain on stone tablets, but these are predicated on the idea that if we have less variance in our text, that the different expressions of things will kind of converge. So accented characters are things like enyes, or vowels with accents over them. And this term ASCII, well, ASCII is a very simplified character set. So ASCII characters are A through Z lowercase and A through Z uppercase, right? There's not a lot of space for accented characters in ASCII. We're also going to remove special characters from our corpus. And again, that's to reduce the variability, to reduce the variance in our text. And then we will perform the process of either using a stemmer or a lemmatizer for our words. And I'm going to explain what this means real quick. Stemming and lemmatizing are 2 different ways to get at the root of the word. That's what stemming is, or lemmatization is. You're trying to get to the root of a given word. And there's a time when you might use a stemmer. There's a time when you might use a lemmatizer. And it's kind of conditional. So I'll cover that once we get into there. we're also going to remove stop words. And stop words are words that are helpful to natural language that give some meaning, like the word the word and. See the word the word in or for. Those are all stop words. And they show up a very high amount in documents, to or a or etc. But they don't add a lot of meaning if we're looking at the statistical frequency of words, right? If the word or shows up a lot, that doesn't mean that your document is about the word or, right? So stop words allow us to focus on the signal and pay less attention to the noise. And then also part of the text preparation process, we want to store our clean text for future use. And I think I would argue that it's also a good idea to keep your original text for future use in case maybe you cleaned up too much and you lost some information, or you didn't clean up enough. So I would encourage y'all to cache both the raw original and the clean data. Okay, so let's take a peek at some of our libraries that we're going to be using. Unicode data. Unicode is a type of string. So Python strings are Unicode. And I'm not going to go on a deep dive on different types of string encoding, but Unicode has a lot of options, like a lot of options. Unicode characters include lots of special characters. They include a lot more than just the Roman alphabet, A through Z, right? Unicode also includes other alphabets on planet Earth. It's a very large set of possibilities, and Unicode also includes emoji, right? Which is pretty cool. And we're pulling in the regex library, the JSON library, and from NLTK, the NLTK installed with Anaconda. So when we set up your Python environment, NLTK came with Anaconda, like a whole bunch of stuff like pandas and NumPy came with Anaconda. And we're going to use a couple of different imports from this. We're going to use something called a tokenizer. And what a tokenizer does is it breaks text into pieces. And NLTK also has a pre-built list of stop words. Okay. I'm going to pull in pandas. And then in the curriculum example, we are relying on a Python module, a Python script called acquire. And so the idea behind that is the Python code that's in the prepare is assuming you've already done the exercise for the last lesson. And we've got a function to get articles. Okay, so looking at our first article, we see a title, we see a date. Okay, so what are the math and stats principles you need for data science? Well, the first step in normalizing this text is to lowercase all the things, because uppercase math and lowercase math are talking about the same underlying idea. Same thing with stats, same thing with principles, same thing with data science, right? Like all of these capitalizations are capitalized because this is a title. But when we look at all those actual nouns and verbs, there's no difference in their actual meaning. So we lowercase all the things. Once you've lowercase all the things, it's customary to remove accented characters. Okay, so we have a lot of possibility for accented characters. And the simplest example I'm going to give you is an accented E will convert to an E character. The mechanism that we're going to use here, we're going to use the Unicode library, and we're going to use a couple of different methods. So off of that Unicode library, we're using .normalize, and that's going to handle inconsistency in Unicode characters. And then we've got an encoding step and a decoding step. So let's talk about that. The encoding step here, this is not the same thing as encoding a categorical variable. This is encoding your Python strings to ASCII. And I'm going to pull up ASCII real quick. ASCII is a very simple subset of characters. In fact, it's numerals 0 through 9. It's some punctuation, some math symbols, and it's not very many characters. Right, so what we're doing here is taking a plain Python string, encoding it to ASCII, and that's how we're reducing a lot of the variability. And so we're taking a set of lots of possible characters, converting it into a much smaller set of characters. And then we're decoding and we're turning that back to UTF-8, which is the specific Unicode type of string that Python is. So after normalizing this text, we have, let's see, a couple of the characters remain, like commas remain and pipe characters remain. And I don't see any other specific characters in this example off the top of my head where we've removed them. But basically, if something's not an ASCII character, it has been kind of like downgraded into one. And my example of downgrading that would be taking an accented E and turning it into a plain E character. So far, so good, folks? Nothing too crazy?
I do got a question. In the code block, what does the backwards slash mean?
Oh yeah, this backward slash right here between these pieces of the method chain. That's a good question, Jared. What that's called is a line continuation character. So, or what's going on is a line continuation operation. So if you just type this line of code, unicode.normalize, open paren, close paren, and then hit enter without the backslash and type .encode, Python is going to get snarled up because it doesn't know that the first line is connected to the next line. So you may see this from time to time. And let me see. Do y'all see an editor or do y'all see the browser right now?
Browser still.
Browser still? Okay, give me one sec. Okay, do you all see the editor now? So if we were to not use these backward slashes, that escape character, we would have to put everything on the same line like this. Or alternatively, the other way of doing this, if you wanted to have that kind of method chaining, you could get around these backslashes by doing wrapping that entire expression in another set of parentheses. So really it's another way of writing Python code in a way that doesn't produce an unintended error message. Might be that y'all's first time seeing this, Jared, so that's okay. But y'all have seen lots of like these .encodes, .decodes. Those are just string methods, right? But these continuations are putting at one operation per line is what that's allowing us to do there.
Thank you.
Mm-hmm. Yeah, you're welcome. That's a great question. You saw something new that we hadn't used before, so I'm glad you asked about that. It's nothing like crazy or different that is NLP related or related to this library. It's basic Python that we just haven't seen this kind of style before. Yeah, other questions coming up so far about lowercasing all the things, normalizing, turning your character set from a more complex character set into a much simpler character set to remove accents.
Can you say again the decode and UTF-8? Can you explain that one again?
Yeah, so we're encoding to turn the string into an ASCII string. ASCII has like only a couple dozen characters as opposed to millions, or like UTF-8 does. And then we're turning the string back into a UTF-8 string. So the encoding transforms the letters to a simpler representation, right? So if you're doing NLP on a Czech language, which has a lot of accents, or Spanish that has a lot of accents, all those accents are lost, right? As part of that normalization process. And then just great question, this decode is putting Humpty Dumpty back together again. And by what I mean by that is the string data type is turning back into a UTF-8, like a default Python string.
Okay, thank you.
Yeah.
I might have missed it, but what does NFKD mean?
No effing idea. No, I don't know what that, I actually don't remember what that stands for. We could look it up in the normalize. It's something that's telling that normalize function what to do. So we can look it up. Okay, there's a normalized form. We have a couple of different forms, NFC, NFKC, Kentucky Fried Chicken, whatever. I'm not like prepared to go into all of these different forms. But they're different representations. So we've got a little example here. The Unicode character 00C7 is the Latin capital letter C with a cedilla comment. Depending on the form here, it looks like we could present that as a Latin capital letter C with a secondary character next to it. So it's giving you some more control. For the purposes of your exercises and the project, I wouldn't worry about those different forms. Now, if you were doing a project like an NLP project on, some sort of Finnish language, then you might want to take a look at that and see what that does. Does that make sense?
Yeah.
Cool.
Thank
Cool. Yeah, NLTK is Natural Language Toolkit, is the name of the library there. We usually want to remove special characters as well. Just because you've converted that string into ASCII doesn't mean that we are totally without special characters. So as part of your normalization process, you might use some regex to replace. Let's take a look at what we're doing here. This is matching the regex, anything that is not, remember the caret inside of the square brackets is not. So this is saying anything that's not A through Z, 0 through 9, literally an apostrophe, or \s. \s is a space character. What this substitution is doing is replacing each one of those characters with an empty string. So a string of length 0. Okay, so we lost our commas, we lost the pipe character, we lost a whole bunch of characters here, right? And there was some mathematics that was going on, or some math notation down here in explaining this blog post was talking about commutativity and associativity. So this had equal signs, this had parentheses, those are gone now, right? And that's not the end of the world here, because like we weren't trying to parse and figure out what the math was doing. What we're trying to do is normalize the text itself, right? And sometimes you might see little artifacts where something's not perfect, like this word growth decay. was never the word growth decay. It was the word growth, probably a / and then decay. And so that / was replaced with nothing, with an empty character. So if you have some kind of weird artifacts in your NLP, that's totally okay, because it's never going to be perfect just because language is so funky, right? Natural language is awfully funky. Right. Another tool that we could use is, or a step in our process that you should consider, is this process of tokenization. And this doesn't mean that you go to Chuck E. Cheese and you jam $20 in the machine and you get a bunch of worthless coins that are worthless outside of Chuck E. Cheese. What this is talking about is this term token is talking about words and discrete units of words. So let's talk about this a little bit. This tokenizer we're going to use from Natural Language Toolkit. There's a couple of different types of tokenizer, and the tool that they have that we're using here is called the tokenizer. And some things that this might do is, if you haven't already removed, if you've chosen not to remove your special characters, your tokenizer is going to do things like take a hyphenated word and bust it up into 2 words, for an example. And if you still have any punctuation left over, the tokenizer is going to break out a word that's next to a period. It's going to break the period away from that word, because the period doesn't belong to that word. It doesn't add any extra meaning. Okay. So you might consider, I realize the tokenizer is happening after we've removed some special characters. You might want to play with this in the exercises and run the tokenization first, because things like this, and I just realized this, things like this growth decay, which used to be 2 words separated by a / the tokenizer is going to bust those out into 2 words, and it's going to bust out words from their punctuation as well. Cool. So again, all of this normalization, what's really going on with lowercasing, with removing special characters, with all of this normalization, all of these normalization steps, we're reducing variability in the text. And that's really based on a fundamental assumption that when you reduce variability, especially with things like lowercase and uppercase, you're getting to the heart of the matter and you're not losing too much data in the process. Okay. Questions so far? Tokenizations, lowercasing, going between different kind of character representations.
Question: the tokenization,
Yeah.
it specifically calls out, says after moving non-ASCII characters, but you can do it in either order, right?
Mm-hmm. Yeah, if, like, let's say you called your tokenizer first, the tokenizer would still have ASCII characters, but those ASCII characters would be broken out as a separate piece from the word. So, and like my encouragement here is to play with the order, and it'll, like this non-ASCII right here. See how that's a hyphenated word? I don't have a notebook running right now, but I'd be willing to bet you if you put non-ASCII into the tokenizer, you would get back the word non as 1 string, the dash is 1 string, and the ASCII is 1 string.
Thank you.
Mm-hmm. And tokenizers, if you use the tokenizer, you might get back either a string or a list of strings. Notice in this tokenize function, you're saying right here to return the string, not to return a list of strings. So you're giving yourself a little control over that. Cool. Up next is this concept of stemming and lemmatization. And this is really an either or scenario, or you could do both. Both stemming and lemmatization they're really after the same thing, and they take a different path to get there. So what we're trying to do is we're trying to get to the root of a word. And because I mean, English more so than any other language is wacky as heck, right? English is super wacky of a language. We have some simple rules for getting to a stem of a word, for getting to the root of a word. And so stemming is going to do kind of the simplest, dumbest way of getting to the root of the word possible. So I'll give you an example. The word calls, the word called, the word calling all share the base stem of call. So what a stemmer is doing is it's following a much more rudimentary set of rules to drop ed, to drop ing, to drop plurals, right? Or s. And there's a couple of different stemming algorithms on planet Earth. The example in the curriculum is going to use the Porter stemmer, named after its inventor. And what you'll see is that stemmer gets to the root. So the root of, or the stem of call is call, the stem of called is call, the stem of calling is call. So again, this is predicated on the idea, this is all based on the idea that by reducing variability, you're getting to the heart of the matter and increasing. So if you had a bunch of different words that were all about call or running or programming, all of the different endings aren't adding extra information, but the more frequently you see the word call come up, or the word run come up, or the word program come up, that's telling you that that document's about running programs, or that document's about making a phone call or something like that. So don't be surprised when you see kind of incomplete words coming from a stemmer, right? Principal, PL, science with no E at the end. This is probably taking like the stem of science, the stem of scientific, etc. And I want to kind of drive home this idea that stemming is following a very simple set of rules, very, very simple set of rules. The upside to following a very simple set of rules is that it takes less computational resources. So let's say you had, I don't know, multiple terabytes of text, a stemmer is going to run faster than a lematizer. So that's why we're introducing both of these at the same time. So stemming runs faster, but it's quicker, but it's also dirtier. And then lemmatization, on the other hand, is going to be a little bit more sophisticated of a set of rules. And because English is wacky, we have a whole lot of different rules. And I'll give you an example of that. These both exist on Natural Language Toolkit. The WordNet Lematizer, what this is doing is, and we can take a look at this code, we have a sentence here. He was running and eating at the same time. He had a bad habit of swimming after playing long hours in the sun. And in the for loop that iterates across this sentence, so what we're doing is taking that sentence and splitting it on the space character. So we have a list of strings, and then we for loop that list of strings there. And notice what we're doing. We're printing out the stem of that word, and then on the same line, we're printing the lemma. And so some of these things are going to be pretty similar, right? He and he, wa and wa. The stem is run from running, but notice how the lematizer is, it's not just lopping off the end of running. Same thing with eat and eating. Some of these are the same, swim and swimming. So lemmatizers are doing a little bit more computation per word, like a very minuscule amount per word, but that's going to add up if you have like, you know, if you're trying to process the Library of Congress or something crazy like that. Here's another example of a different string studying what they needed to study. The students studied studiously. Say that 5 times fast. Now the stemmer, study with an I, that's not even a word in the dictionary, right? So the stemmer can be a little bit more blunt. And when we look at the lemma, it's still reducing some of the variance, but you're getting a little less nonsense from a lemmatizer. Okay. So like if you ask me, Ryan, what do I need to do? Do I need to stem then lemmatize, or do I lemmatize and stem? For the exercise is going to have you use both to get you practice with both. But in practice, it really depends on how large of the data set you have to work with. If your data set fits in memory on your laptop, I would just lemmatize all the things. If the data set is so large that you're having to pay AWS or pay for like a cloud computer, I'd probably crank out your MVP with the stemmer first, if it's just such a huge data set. Does that make sense? The computational difference? Cool. Either way, stemming or lemmatizing, we do want to remove stop words, and stop words have very little or no significance. And there's a list of stop words in, actually, Natural Language Toolkit gives you a bunch of different spoken languages, but we can use .remove to remove a stop word. And we can also extend the stop words. So here's an example of some built-in stop words. I, me, my, myself, we, our is ourselves, you, your. And this is just the list of the first 10 stop words. There's a whole bunch of them. So stop words are really just noise compared to the topics in your corpus, in your text data set. Okay. Let's see. In this last little bit of example here, what we're doing is we're taking the string that contains a blog post article, we're splitting that into a list of strings to make a list of words. And then notice this filtered words list and this list comprehension. This is saying return all of the words if they're not in the stop list. So if the word was in the stop list, it's filtered out by means of this list comprehension. And so we get a list of the filtered words. And what we're saying right here is we removed X amount of stop words. And then the computation for that is however many words that were in your original string minus the number of those filtered words gives you the number of stop words that were there. So from this one article, this is just one article, this list comprehension removed 240 different stop words. And that's important because our text, the real goal of natural language processing is to figure out what the heck the text is about. And we don't want to incorrectly come to the conclusion that the text is about the letter I, right? Or the word we. So stop words are pretty important at filtering out that noise. And then when we look at this one particular article, this might not make a lot of sense in English. Math stats principles need data science, October 2020, data science coming, data science program. Need no math stats, however many applicants actually learn application process, don't need expert applying data science accessible field, anyone dedicated learning, right? That's not really proper English. But if we are building a, like when we get into the modeling component, or actually the exploration component that we'll do tomorrow, we don't need to be focused on the frequency of things like stop words because that's noise. And we need to be focused on things like the frequency of the word math, the frequency of the words data science. And we'll talk about this a little bit more tomorrow, or actually we'll introduce this concept tomorrow. We can look at pairs of words together, like data science, and see if that's a word pairing that comes up a lot. It sure looks like it's coming up a lot. So that's a pretty cheap way of knowing that this article is about data science if that word pair shows up a whole bunch, right? That's one of the ways we can come to understand the content of some text. Because there's like, no matter how much machine learning we're doing, there's no actual cognition going on. There's no thinking going on in these algorithms. It's just stats and math, right? Cool. So these exercises are, oh yes, I see a question from Jess. Go ahead, Jess.
I was gonna ask, is there a way to pre-game the filtering? So like, say I'm doing a study and it's on like medieval times and I don't want all my kings to turn to K kind of thing. So like, if you know something, a topic of interest might be affected by these filters, is there
Oh, yeah.
like a method or strategy for kind of pre-gaming your data before you apply the filter? So it doesn't filter out words that you know are important?
Oh yeah. Like right here, the stop words list. If you wanted to say, hey, something is not a stop word, you would take that stop words list and remove a specific word from that stop words list.
And can you do the same with the one that does like the INGs and the limits and the,
Not to my knowledge.
okay, so
Not
those
to
are
my
as,
knowledge. Yeah.
okay, thank you.
Cool. The exercises, there's a nice pile of exercises here, about 9 of them, but they're pretty straightforward. I'm sorry, go ahead. Thought I heard something. Okay. These exercises are going to be pretty straightforward. You're going to make a basic clean function that lowercases all the things, normalizes all the things, and uses regex to replace things. You'll make a nice little wrapper function for the tokenizer. And what I want you all to do with that tokenizer is play with it. Play with tokenizing before cleaning, play with cleaning before tokenizing. I want you all to have some experiential understanding, some experimental understanding here. And then we're going to have you stem all of your blog posts and articles, lemmatize all your blog posts and articles, make a function for each of these, remove stop words. This remove stop words function, actually speaking to one of Jess's questions, how can you control what's a stop word or not? The exercise is going to have you build that functionality where you can exclude words from being stop words, or you could make extra stop words. So I'll give you an example of when we might add a stop word to the existing stop words. If we are scraping the code up blog, I would argue that the word code up is a meaningless word because we already know that all of the dang blog articles on the code up blog are about code up. So that we can take that word, that string of code up, and add it to the list of stop words that we can effectively ignore for our analysis, right? Just like if we were, I don't know, doing NLP for Amazon, we wouldn't want to have the word Amazon as part of our analysis. We could add it to the stop words. And then we're going to make some happy little data frames. We'll make a news data frame and a code up data frame. And for each one of these, we'll produce the following columns: the original title, the title, the original text. So you have the raw, the clean text, which is normalized and tokenized, a version of the stemmed text, and then the lemmatized text. And then on exercise 9, we've got a kind of a thought experiment. If you only have half a meg of text, which would you use? If you had a quarter, if you had 25 megs, how much would you use stem or would you lemmatize? And what if you had 200 terabytes? So that's a lot of text, right? So I'm going to bring our recording to an end.